Okay. So we are going to start with the work concept. So, I mean, this is our fundamental concepts for the energy. And then we are going to build upon this. So we are going to then define the kinetic energy and then the potential energy and so on. So one by one, we are going to build on the things that we define. At the end, we are going to have some kind of a solid understanding of an energy concept. Okay, so that's one of the fundamental concepts in physics. Later, you're going to learn that in classical mechanics, for example. You're going to learn that if you can write down the energy of a system as a function of velocities and positions and things like that, then you also know you can determine the dynamics by just looking at that function, right? That's basically more or less what it is. So that's one of the reasons why the energy concept is very important for us, right? Let's start with this work concept. So it's basically work done by a force. You can actually state it like this, but I'm also going to state it in different ways. So basically, we have some kind of an object in here and a force applied on that object. And the object displaces. So let me show this with a different color. So delta R is the displacement of the object. Okay. So work done is basically expressed as the dot product of the force with the displacement, right? That's the first place that we actually use the dot product in physics. I mean, I've used in deriving some certain things perhaps in the past, but this is the first place that it appears. And it is not easy to explain the physical meaning based on the geometric meaning of the dot product, right? Just keep this in mind. But what's important in here is that the force is a vector, right? And the displacement is a vector. So we have a product of two vectors in here. There are two types of products. So I can take a dot product or a cross product, but one of them gives a scalar and the other one gives a vector. Here, the result is a scalar. So as a result, the product should be a dot product, right? That's the only thing that I can say right now. And that's one of the common, let's say, mathematical relationships that you're going to see in all the physical relationships that you're going to see from now on, right? So somehow these expressions are consistent with the vector and scalar nature of the quantities, okay? So in any case, so this is a scalar concept, right? So that means that's just a number, but that number can be positive or negative. Just keep this in mind. So we don't object a number being negative. There's nothing wrong with a number being negative. In any case, so the dot product can produce negative and positive results, right? Let's just remember a few things in here, right? I can express this dot product in terms of the, in terms of the magnitudes and the, let me write the vectors in here, and the angle between them. So I can write this thing down as the magnitude of the force. Yeah, let me use this absolute value sign, right? This delta R, yeah. I mean, normally I should put an arrow in here, right? It's the magnitude of a vector, but in any case, this is just a scalar multiplied with cosine theta. Okay, so that's the, let's just remember that that's the one of the properties of the dot product. Or if I have like an X, Y, Z axis and I have the components of these vectors, I can also write this dot product as the product of the components of these two vectors. Products of the components added up for these two vectors, right? Just keep this in mind. I mean, this is our definition. These are just alternative ways of expressing this dot product by using the various properties of these vectors, right? This is written in terms of the magnitudes and the angle between the vectors. This is written in terms of the components. Okay. There's another thing in here. I'm also going to talk about the units, sorry. So there's another thing. I mean, this is only if, let's say it like this, right? Work done is equal to F times the displacement. But the displacement of the object might be complicated like this, right? I mean, the object might move like that. But in that case, we are going to count this as the displacement in here, okay? So let me use a different color for the force now. So if the force is constant, if the force is constant, so that means it has the same magnitude and direction everywhere on that path. In that case, that's the correct formula. So let me say it like this. This is if the force F is constant. So under constant force, that's the expression. If the force is not constant, so that's the situation that I'm going to describe in here. So we have a displacement like that, but the force is like this. Let's say, I don't know. Let's say it's like that, and then it changes its direction and then whatever. So at some point, it also changes its magnitude, let's say. I don't know. It's something like that, let's say, right? So it changes its magnitude and the direction. In this case, what you need to do is to basically convert this into an integral. So what you need to do is to divide this path into infinitesimal displacement. So this dr is an infinitesimal displacement. Okay, so divide the whole path into such small displacements, right? In any case, so the work done would then be basically it at each infinitesimal moment, it is force dotted with the infinitesimal displacement. We need to integrate, right? But let me just add in here, if the force F is not constant, either in direction or in magnitude. Hopefully we don't need to evaluate these kind of integrals in here, but we will have to, because I mean, for two forces we are going to do the integration, but I'm just going to handle it in a quick manner. So as a result, I'm going to postpone these kind of calculations to the next chapter. So for a spring and for the gravitational force, we need to do this integration, but I would like to do this within the context of the concept of potential energy, right? I'm not going to do it at the beginning. So most of the time we are going to do this. Okay, so let's talk about the units of work, let's say. So it's basically, since just the product of a force with a displacement, it is Newton meters. So therefore it's kilogram meter squared per second squared. Since this is a common unit that we use a lot, we just call it with this name, joule, and show it with the capital J symbol. All right, I'm just going to write it in here. So you're going to learn about Joule and his experiments later in the 4th year. He's basically is the one we created him actually with the first law of thermodynamics. First law of thermodynamics. It's basically the conservation of energy. I mean, he has done some experiments that established the statement of the conservation of energy in a broad sense, actually. In any case, we will see the conservation of energy in the next chapter. But in any case, to honor him, actually, we just call this unit as the Joule unit, right? So since it's named after a person, the name of the unit is always written in capital letters. But if you remember, the long name of the unit is somehow written with a small letter. All right, let's just keep this in mind. Okay, what else? So in any case, we have these kind of situations in here. So if you're applying a force like that and the displacement is more or less in the same direction, where the angle between the force and the displacement is less than 90 degrees. So in that case, work done is positive. Okay, so it's a positive work done. But then there are these situations where the force is like that and the displacement is like this, right? In that case, the angle is equal to 90 degrees, in which case work done is equal to 0, right? It is this situation. Let me separate these situations like that. And then we have a situation where you just push the object like that, but the object moves in the opposite direction, let's say, or with some angle to that direction. So let me actually kind of show it like that. So in that case, the work done is negative, right? So we say negative work done. Okay, so let me just separate them like that. So it's a scalar quantity, but it can be positive, can be 0, or can be negative. Okay, there's nothing unusual in here. Let me drink some coffee. What else? Yeah, I was going to say something else. Yeah, the name, sorry about that. So probably I should have explained this at the beginning. So we have like object A. And then object B in here. Okay, so we might have like forces applied on the object B. So I'm going to show it like that. So that's F. So let's say that F is the force applied by A on B. So it's some object applies the force and the force is applied on the other object, right? So as a result, the work done here is the force dotted with the displacement of B, obviously. So that's the force applied on B, and that's the displacement of B. So that's basically a property of the object B. So I can actually say it like this. This is work done by the force F. That's basically the first statement that I have used. I can also call this as work done on B, or I can say that this is the work done by A. And I think the most complete statement would be like work done by A on B. Okay. So as a result, I mean, I will be using any of these 4 ways of labeling the work concept, right? Just keep this in mind. I think I'm going to, if possible, I'm going to prefer the last one. So it's basically something is doing the work on something, and we are going to see that this is more or less, there are some certain subtleties in here. It's basically the energy transferred, let's say, from A to B, more or less, right? Again, there are some subtleties in here. I don't know, if we just meet these kind of things, then perhaps we can talk about them. But as a result, I mean, this is how you may imagine that work, when basically A does a positive work on B, somehow some energy comes out from A loses some energy, and B gains some energy. So it's basically a transfer of energy from one object to the other one. That transfer might be positive or negative. And so as a result, I mean, if it is negative, then we just, I mean, the equations will still be the same at the end. In any case, at this point, we cannot say anything about this interpretation here because we just defined the concept. We are going to relate this to the energy of the objects A and B later, right? Not at that point. Okay. So I don't know if there are any questions in here. If there are questions, then I cannot see them, obviously. So let me open the chat screen. Okay. There is this classical, so that's the work done by gravity, right? By gravity. So we have some kind of an object. There's gravity downward. And let's say that this object is basically, I don't know. So let's say that this is a projectile. So therefore it just moves like that. Okay. And force is not negative. Right. Let me do this first. Work is mean. Work is negative. So work negative. If I do a negative work, basically, if I do a negative work on B, let's say, energy of B decreases, my energy increases. So it's basically an energy transfer, but in the opposite way, right? If I do a negative work on B, B does a positive work on me. So as a result, the energy flow is from the other way around, from B to myself. Okay, so let's think about this kind of motion. I mean, this might be a projectile. So let's say that this is the initial point, that's the final point, right? The gravitational force is constant in here. So let me show it like that. So that's mg, so that's constant. And then we have the displacement like that. Okay, so that's delta R. Okay, so I can then, therefore, I mean, in this kind of a situation, for example, let's say that the altitude increases by h. Altitude increases by h. So what's the work done in that case? So that's the dot product of mg with the displacement. Okay, let me just write this thing down like that. I think I'm going to put a reference frame in here. Let's say that the x-axis is horizontal and the y-axis is vertical. So in that case, I'm essentially, what I do is like in that case, let me do it like that. So in that case, I can separate the displacement into these two components, right? And this dot product is equal to 0. Okay, because these two vectors are perpendicular to each other. So in one case, the displacement is horizontal and the force is perpendicular to it. So the angle between them is 90 degrees. And so therefore their dot product, this particular dot product is equal to 0. The other dot product, this one in here, mg is pointing downward and the displacement is upward. And so therefore, since they are opposite to each other, therefore the work done is equal to minus mgh. So in this situation, the work done basically is given by that expression. You can also find this quantity without using a reference frame, obviously. But in any case, I mean, you have to do this only once, and after that, we are going to keep using the same expression, actually. So in any case, let's just say that in here, work done does not depend on the horizontal displacement. And the reason is that the force does not have any horizontal component. It just has a vertical component. And so as a result, I mean, at least for this, yeah, let me draw this thing actually. So this is the motion in here from initial point to the final point. But then I can think of this as a motion like this. It's just in the vertical direction. So as a result, this motion, for example, to a different final point in here, let's say, I don't know, let's call it as A. Why did I call it like that? Yeah, I'm just showing the picture in here. I'm not doing anything serious, all right? So in this situation, the force is downward, but the displacement is upward. Okay. So as a result, in that case, the displacement is h. Force has a magnitude of mg. So let me also remove this arrow in here. So as a result, since these are opposite in direction, work done is, in this kind of a situation, is basically mg times h times cosine of the angle between them. But that's equal to -1, so therefore that's minus mgh. Okay, whatever it is, I mean, displacement is upward and the force is downward, so therefore the work is negative if the altitude increases. If it decreases, then the work done would be positive. So the work done depends only on the altitude change. In all of these problems, in this particular case, for example, if it's a projectile, then the object is moving only under the effect of the gravity. Okay, so as a result, even in this case, it is possible that the displacement is opposite to the force, okay? Because force only determines the direction of the acceleration. It doesn't determine the displacement. So if the object has some initial velocity in the opposite direction, then it will have an opposite displacement, right? But there will be situations where it won't be just the gravitational force, but many other forces will be acting on the object. So as a result, the object might be doing very complicated motion. In any case, in all of these cases, this displacement should be considered as a quantity which is completely independent of the force in here. So it's basically we are computing a particular type of force and work done by that force on the object. So as a result, this is the gravitational work done. And you can also think of it as the work done by the Earth on this object. Okay. I have this stupid question. All right, it's stupid because it's supposed to be conceptual. So I lift an object, let's say with mass, it's like 10 kilograms, let's say, object with mass 10 kilogram. I lift an object by 1 meter, carry it 100 meters horizontally, and lower it by 1 meter. How much work did I do? I mean, this is like the motion in here. So there's this object in here. I lift it up. This is basically, the height is 1 meters. Move it horizontally by 100 meters. And then lower it by 1 meters. Okay. So the object has mass 10 kilograms. So let me write m equals 10 kilograms in here. Forget about it. So we know what the mass is, right? Okay, so how much work did I do? Why do I ask this question? I would like to compare this concept of work with the everyday use of the word work, right? Because this is a word that we use in our everyday life. And when we use it, we actually mean something else. If we are using it in physics, it means something else, right? On the object. Let me add this, right? Okay, so I think I can kind of explain the things in here. But in any case, I can assume that all of those lifting and then carrying and whatever, these kind of things are done at constant velocity. So assume lifting up, carrying, and lowering down are done at constant velocity. Okay, so it's basically these parts of the motion. So let me use a yellow color for that. So that's the first part, that's the second part, and that's the third part. Obviously, there has to be some acceleration of the object at this point, and at that point as well. And also there should be an acceleration when I'm starting lifting the object up, because initially the object was at rest. Finally, it is moving upward. So there is an acceleration in there. So as a result, the net force is not zero in there. But I'm just considering the other region. So let's just assume that the acceleration is done in a very short displacement. So I just quickly accelerated this thing. And then when it is going up, it was just moving with constant velocity. And when I'm stopping, of course, I also stop it immediately. So as a result, the displacement would be negligible in such cases, okay? It's just an assumption, but that's not going to change anything. Basically, what I mean by this is that the net force is equal to zero, right? Which means that at any point in the free body diagram, the force applied by my hand and the force applied by the gravity, they are equal to zero. Okay, so my hand applies a force which is equal to the weight of the object. Does it matter for the solution if there is an acceleration or not? No, it doesn't matter. At the end, if I didn't drop it, okay, if I just lower it to the ground and then make sure that it is at rest and I'm holding it all the time, then it doesn't matter. That's basically work kinetic energy theorem that we are going to see in the second hour. Okay. In any case, so this then tells you that the work done by the hand is basically is a constant force. It's always upward, right? Even if I'm carrying it horizontally, work done by the hand is always upward. Okay. So as a result, that's what I'm going to do. I'm going to say that work done by the hand, right? Let's just say it like this: work done by the hand in the first part of the motion plus in the second part of the motion plus work done by the hand in the third part of the motion. Okay. In the first part, I'm lifting it up and the displacement is up. I mean, the force and the displacement are both up. So therefore, the work done is positive. So let me just call this as this distance as h actually. That's 1 meters. In any case, so the work done is positive. I do a positive work. So when I'm carrying, I'm basically lifting it up again, but it is moving in the horizontal direction. The displacement and the force are perpendicular to each other. So that angle is 90 degrees. And so therefore the work done is equal to 0 in such a situation. Finally, when I'm lowering down, force is upward, but the displacement is downward. So therefore the work done is equal to 0, is minus mga, sorry. And so that means the total work done by the hand is equal to 0. Which means I don't do any work. I don't do any work. Okay. So as a result, this is kind of confusing, right? Because, I mean, we kind of assume that the physical work concept is somehow, well, captures the essentials of what we call as work, right? So we don't do any work in here. And the question is, right, then why do we get tired if we don't do any work in here? Why do we get tired? I mean, let's just reconcile these two concepts of physical work done and the work concept in everyday life. I don't know if you have any ideas in here. Gravity also has zero work done in here. In that case, the signs would be the opposite. So at the first part, the work done by gravity would be minus mgh. It is 0 in the second part, and in the third part, it will be positive. Okay, so it's just the opposite in sign, but the total work done by the gravity would also be 0. Is there an internal energy situation on my side that I don't transfer to the object? Well, everything has an internal energy. All right, let me just say it like this. I mean, when I am doing something, when I'm lifting an object up or lowering it down, doesn't matter, for lowering down as well, what happens is that my muscles are also doing something, right? There's some kind of a displacement in there too. So when I'm lifting an object up, or applying any force actually, not applying any force, sorry. When I'm lifting an object up, that's not the only work that I do, right? I'm not doing work only on the object. My muscles also doing some works on these muscle cells as well. So as a result, there will be some work done in this part of my body, as well as a work done on the object, okay? So somehow I have to spend energy to actually transfer to the object and also transfer some of this energy to my muscles as well. Okay. So at the end, when everything is finished, the network that I did on the object is 0, but the work done on my muscle tissues would still be positive. And as a result, my body will feel the effect of this. Okay. So that's why I added this, right? How much work did I do on the object? So the answer is 0. And there's nothing wrong, nothing confusing about this. But how much total work did I do, right? On the object and on my body? In that case, the answer is positive. And this is basically what tires us, right? I mean, let's just try to explain it like this, because that's kind of important. In a way important, because I mean, usually we actually forget these kind of things as well. When some machine, for example, does a work on something, for example, there's also some kind of something going on inside the machine as well. And there are situations where you also have to take these kind of things into account as well, right? But in any case, that's kind of a nice example. So when you are lifting something up, you're doing positive work. And when you are lowering down, you are doing a negative work. But you're doing a negative work on that object when you are lowering it down. So still for you, this might be tiresome. And so as a result, there's something else going on inside your body, so that this job, for example, may also appear to be hard for you too. Okay. Let's just keep this in mind. Okay. So the next thing is the work kinetic energy theorem. All right, but let me first do this, okay? So you have some kind of an object, right? Object A, okay? And then there are some forces acting on this. So there's F1, F2, and so on. I don't know, I mean, let's just say like Fn in here. Fn, right? So N forces, N different forces. As a result, the net force on the object is, this is F net. So it's basically the vector sum of all of these forces. Okay, so I'm going to also consider the case where these forces may not be constant. So as a result, I'm then going to think about this possibility. In any case, I'm going to think about the possibility that these forces may not be constant. So I'm going to consider some kind of a motion of the object. So I don't know, it's just accelerating, right? So I don't know, yeah, let me just say it like that. So it basically moves along this path, right? So there's some kind of a displacement in here. So that's the motion of the object. So let's say that this is the trajectory. Okay. So if I want to compute the work done by the force F1, all I need to do is to evaluate this, this integral. We are not going to evaluate it. So that's the work done by force F1, okay? And I can continue with this work done. I mean, I can compute the work done by each force separately. So as a result, I'm going to compute a separate scalar quantity for each force, okay? Let's just do it like that. So the final one is Fn. All right, let me repeat these. This is Fn, okay? Or I can sum them up. So therefore, this is like the total work done by all of these forces. Okay, in that case, I need to add them up. Fn dot dr. So this integral is also added up, but I know that the sum of all of these works done is basically the net. Sorry about that. Okay, I'm adding all of these integrals, right? Since all of these integrals, the displacements are the same, but the forces are different. I can do that, right? I can do a summation of the forces first, and then take the dot product with the displacement, okay? But I know that this is equal to the net force, okay? And so as a result, the right-hand side is the net work done. Okay, so let me write this thing down like that. So that's the expression that I'm going to use. When I say W net, I actually mean one of two different things, but basically they are the same, right? So that's the work done by the net force, F net, or it is basically the sum of works done by all forces, which is basically the work done by the first force and the work done by the second force and so on. So in some situations, it might be easier to compute this work done by just computing the work done by the net force sometimes. And sometimes it might be easier to do it like that. Usually it will be easier to do it like this. But in any case, both of them actually mean the same thing. Okay. So the work kinetic energy theorem basically relates the net work done to the change in the kinetic energy of the object. So let's have a break. After the break, we are going to give this as an example. I'm going to prove this as a theorem. And then we are going to solve a lot of problems, a lot of complicated problems, actually, that we cannot solve by Newton's second law alone. So as a result, this will kind of tell us the usefulness of the work concept, okay? So as a result, we will spend some time with the work kinetic energy theorem, but that's one of the fundamental things, fundamental relationships. So far, this is just a concept. Now we are going to see how to use this concept.